All right, let's get started with Ampere's Law. So with Ampere's Law, you will see that it's very easy now to solve a lot of problems that we were trying to solve with Biot-Savart law. The Biot-Savart law is what we use to do a lot of problems in finding the magnetic field of a current at some point in space. But you can see how tricky that law is to use. But with Ampere's law, we're able to take advantage of symmetry. So if you have an infinite straight line, or if you have a solenoid or toroid, we can take advantage of the symmetry involved in those geometries in order to find a magnetic field at some point in space. So it makes it pretty straightforward when you use Ampere's law. Okay, so we'll say Ampere's law allows us to make use of symmetry to solve problems. This is easier than the Biot-Savart law. So we can say that when we have an infinite straight line, also a sheet or an infinite sheet, a solenoid, and a toroid, we can use Ampere's law. So what is Ampere's law? So for Ampere's law, we'll take the integral of the line segment. So we can say, let's do Ampere's law here. So let's consider the straight current carrying wire, or current I. So we have a current carrying wire like that. So the current through the wire is I. And so by right-hand rule, if you grab the wire with your right hand, then the magnetic field at this point is coming out of the board, and it's going to be into the board down here. Okay, so we can think of a loop like that. So the field is out at the top here and in down here. So we can think of looking at it endwise. This is our side view. If we look at it from the end, then we can say that the current is this way into the board, and then we have the magnetic field that way. So if the current is in, then the magnetic field is going to be pointing this way at the top and that way. Okay, by right-hand rule, if you grab the wire with your right hand, then your fingers curl in the direction of the field. So current is in, and this is the magnetic field B and B. So this distance is R, so this is the radius R. So if we take a segment of length dl here, then we can see that we will take a line integral around the closed loop of radius. The loop is called an Amperian loop, and it encloses a current I. So the magnetic field at a point is given by let's do it this way. So the integral over the closed loop of B dotted with the line segment dl is equal to the current enclosed, mu naught times the current enclosed. So I enclosed is equal to current in the Amperian loop. So if we just think of, so using our diagram that we have there, you can see that the segment of length dl is parallel to the field B. So if we take a dot product, the dot product will give you 0. dl B times B dotted with dl gives you B times dl cosine 0, which is 1. Okay, so the integral here will just be B. We can take B out and then take the integral over the closed loop and say that's equal to mu naught times current enclosed. And so if you look at that loop, what is the integral over the closed loop going to give you? So the integral over this loop, what does that give you? Should just give you the circumference. So it's going to be B times 2 pi r, where r is the radius of that loop, and that's equal to mu naught I enclosed. So the magnetic field B is just going to be equal to mu naught I enclosed divided by 2 pi r. This is I enclosed. I enclosed is just equal to I, so you can remove that and just write B equals mu naught I over 2 pi r. So what we've done is we found a magnetic field at some point in space next to a current carrying wire by defining the current enclosed, or by taking the field, the integral over a closed loop called an Amperian loop. And so this is basically what we do when we use Amperes law. So we'll say that we found B by using the integral over the closed loop, and we say this formula for B is the same as what we found with Biot-Savart law for a straight wire, okay, for a straight wire. So if you recall, we used Biot-Savart law, we found the same formula. So this tells us that, or at least this shows us how easy it is to use Amperes law. So let's state Amperes law. So Amperes law says that Amperes law is just that the integral over a closed loop of a certain field B dot dl is equal to mu naught times the enclosed current. So the integral is over a closed loop that we call the Amperian loop. So this is Amperes law.
Oh, why does the integral have like a zero or a none?
Oh, that in there is just the loop. It's just telling you that this is an integral over a loop.
Oh.
That's why I have it that way. So it's an integral over a closed loop. Any questions on Amperes law at this point? Okay, let's do an example where we can use Amperes law now. So the current carrying wire has a radius r and carries a steady current I uniformly distributed. Let me write steady current. What the steady current? Yeah, steady current is important in what we're doing. If the current is changing in space, I'll let you know. When we get to AC circuits, that will be the case. In the AC circuits, the current will be changing sinusoidally or in some other fashion. In this DC, we are just dealing with DC at this point, so the current is steady. So the question will be, let's see, let's calculate the magnetic field. So what we have then is a wire that looks like that. So the wire has radius r that way and carries a steady current I. You can think of the current as going this way. So we'll do, say, because the current is going this way by right-hand rule, then the field is going to be going this way and that way. So we have this is the region R greater than or equal to uppercase R, and then in this region we have another little r. Let me redraw this better so that it doesn't interfere. Okay, so what we have here are two regions that we are interested in finding the field in. Oh, that's not what I wanted. Like I said, the radius is r, so this is this radius r. So this small radius is little r, if you like, and then when we come out, we can find the field outside of this region also from the center. So you can think of this, if you like, also as r. So the question is to find the magnetic field in the two regions, r greater than or equal to uppercase R, which is this region out here, and r less than uppercase R, which is this region in here. So we know how to find the magnetic field outside of the region. We can use Amperes law. So what I've drawn here is the Amperian loop, okay? So we can use Amperes law. So at this point, the field is this way. This is your magnetic field, and it's this way over here, and your distance is r. So you can think of your line segments up here as dl, okay? So you can use Amperes law to find a magnetic field at that distance r greater than or equal to uppercase R. Okay. So there are two parts to the problem. So first, r greater than or equal to r. So we're going to use Amperes law with an Amperian loop of radius r.
You said we would use like the right hand?
No, Amperes law. Amperes law is meaning that we will take the integral over a closed loop of magnetic field B dot dl, and that will be equal to mu naught times the current enclosed by the loop. Okay, so that's Amperes law. So at this point, let me bring this down a little bit. So once we have that Amperian loop, then we come here. Okay, so all you have to do now is take the integral. The magnetic field is a constant field because the current is steady. So when you do integral of B dot dl, what do you have? What is the integral over the entire loop?
B times 2 pi r, right?
Yeah, so the loop is just a circle of radius r. So the integral over the loop is the circumference of the circle 2 pi r. Okay, so the integral is just going to be b times 2 pi r, and set that equal to mu naught. And what is the current enclosed by the loop? There's only one current there. The current enclosed by a loop is I. Yeah, so we put I there. So basically that is all. So if you use Ampere's law, you can see with two lines we are basically done. The magnetic field is just equal to mu naught I over 2 pi r at r greater than uppercase R. So outside of that wire, outside the surface of the wire, this is the magnetic field there. This is just the same magnetic field we've been finding for a straight wire when we use Biot-Savart law. Biot-Savart law took us many lines to do, but this takes us about 3 lines and we are done. As you can see, it's pretty straightforward when you use Ampere's law. Okay, then the next part of it is to find the magnetic field inside the wire. So we are assuming that this is a thick wire of radius uppercase R, and we want to find the field at some point inside the wire less than R. Okay, so we can say next R less than uppercase R. So we take our wire again. As you can see, this is a thick wire like that. And so this is the center of the wire, and so inside this wire we can draw a new Amperian loop. Let's say this loop has radius R, and the entire radius is uppercase R. Okay, and we still have the same current flowing through, and so we are going to use Ampere's law again. Ampere's law says that the integral over the closed Amperian loop of B dot dl. Okay, so again our field is somewhere in here, and the loop is going to have circumference is dl. So let's say we are taking B to be somewhere in here, and the segment is dl somewhere there. This should be equal to mu naught times current enclosed. Okay, and this time, because we have a thick wire, the current enclosed is not going to be straightforward, because the entire current is I, so we have to find a current enclosed. We are told that it's a uniformly distributed current, and so we can say that for uniformly distributed current, we can say our current density J is equal to the current per unit area perpendicular to the flow. Okay, and so we can say that current density is equal to current I prime over the area, let's say A prime. So we can say that I prime is just our enclosed current. Okay, I prime is the current that we are enclosing. Okay, and so the area perpendicular to the flow, the initial area is just I over pi r squared. Okay, that's your full current over the full cross-sectional area of the wire. And then the current I prime is going to be the over the area segment R1 squared, where let's say R1, or let's just use R because we're using R for that. So this is the segment that we are interested in. Okay. Since the current is uniformly distributed, the current density is the same. So we can say that I divided by pi r squared is equal to I prime. Let me rewrite this. It's not looking too nice. This is equal to I prime divided by pi r squared. So we can say that I prime, which is our current enclosed, is equal to I times pi r squared over pi uppercase r squared. So cancel out your pi's, and you should have I r squared over uppercase r squared. So the current enclosed is I prime. Okay, so that is the current in that small region there. All right. So now we are ready to complete the Amperes law. So the integral over the closed loop of B dot dl is equal to 2 pi r, and that should times B, and that should be equal to mu naught I enclosed. So we say B is equal to mu naught I enclosed divided by 2 pi r, and we know I enclosed is I prime, and so we can say the magnetic field B is equal to mu naught over 2 pi r, and I prime is just I times r squared over uppercase R squared, like that. Okay, so we can cancel one of this with that, and that leaves us with B equals mu naught over 2 pi, and then we have R squared I, and then we can put a little r outside. So this is the magnetic field at some point inside that wire. So outside the wire, the magnetic field is just a magnetic field of a straight magnetic field of a straight current carrying wire, and inside the wire, the magnetic field is mu naught I over 2 pi r squared times r. Any questions at this point? This is for r less than uppercase r. Okay.
So what was the value for mu again?
Mu is 4 pi times 10 to negative 7. So if we plot a graph, plot of magnetic field B versus R, so we can plot a graph here. So the magnetic field, so the magnetic field goes like this. So B is proportional to R. You can see that this whole thing in the parenthesis is a constant, so the field is proportional to R inside the wire, and then outside the wire it falls off as 1 over R. Okay, so here, this is outside, that's too steep, so B is proportional to 1 over R, and B is proportional to R. And at this point here is the surface of the wire R. So this is inside. Questions on that?
You say inside and outside, just the radius?
Yeah, inside the wire itself and outside the wire, because the wire has it's a thick wire. Okay, so another thing we can use Ampere's law for is to use it for a solenoid. So let's try Ampere's law for a solenoid. So let's do it here. So B field of a solenoid. So let's start off by saying what a solenoid is. A solenoid is a way, or it's a device. Let's say a solenoid is a device. So if you look at the magnetic field of a current carrying wire, it's a curved field. It curves around the wire. If you wanted to get a uniform field, you would have to use a solenoid. Just like we did for the capacitor, when we started off with a capacitor, we said a capacitor is a device for creating a uniform electric field in space. Because when you put two parallel plates together, the field between them is a uniform field. In the same way, if we wanted a uniform magnetic field, we will have to use a solenoid. Okay. So let's try that. So the solenoid consists of coils of wire wound in space or on a soft iron core. So you can certainly wind the wires in space or on a soft iron core. So we can do it as below. So let's say we take a coil of wire and just wind it around in space. So this is a space wound coil. Or we can take a piece of soft iron like that. It's supposed to be uniform, so just ignore it. So we can wind the wires around it like that. So this is wound around a soft iron core. And what this does, of course, it makes this soft iron core a magnet, right? So let's say we tap the current going through this way. Okay, so at the top, the current is into the board, and at the bottom, it's coming out. Okay, so by right-hand rule, the magnetic field is uniform in the solenoid that way. Points this way. Okay, in the same way, we have the current going out that way. So by right-hand rule, the magnetic field in this solenoid is this way. So this is B. Okay. So there are many ways you can use the right-hand rule. So imagine that, so that's what I have drawn on the board. So if you think of it that way, so this is a solenoid. So we can find a magnetic field at some point in the field, in the solenoid. Okay, so we can use Amperes law to find B inside the solenoid. Okay, so the current is certainly, let's just take I to be the current. Okay, so for Amperes law in the solenoid, let's do it this way. So I'll redraw the solenoid here. Let's just do the air wound solenoid. Okay, and so since the field is this way, uniform field in the solenoid. Okay, so if you've gone to the hospital and you've done MRI, the MRI magnet is also a type of solenoid, and so they put you in that tube. The reason they use that is because the field is uniform in the tube. So that would be a way to do it. So that's a uniform field in there. That's what a solenoid allows you to do. Okay, so for Amperes law, we can take an Amperian loop like that. This length here is L, and inside is L, and let's put L prime here. This is the magnetic field B. Okay, so B is 0 outside. So outside here, the magnetic field is 0. So if we take Amperes law, we take the Amperian loop, and we say the magnetic field B dot dl should be equal to mu naught times the current enclosed. Okay, so this is inside the solenoid, because inside here we have a magnetic field and a segment dl. This segment dl is right there. So we can say that I enclosed is equal to Ni for n turns of the wires enclosed by, for n turns of the wires enclosed in a region length L. Sorry, lowercase l, not uppercase. Length L, like that. Okay, so this region is what we are talking about. This region has length L, and there are n wires in there. Whatever count, we have n wires in there. So the current enclosed is n times L. So we can say after Amperes law, B times L should be equal to mu naught n times I. Okay. And then we'll say that the magnetic field B in the wire is equal to, in the solenoid is mu naught n over L times I, where uppercase N over L is equal to lowercase n, which we call the number density. So the number density N is the number of wires per unit length, number of turns of wire per unit length. So the magnetic field B is therefore equal to mu naught lowercase n times I. So this is the field of a solenoid. You can see it's a uniform field. It depends on the number of turns per unit length times I.
So the number density?
Yes, number density of turns per unit length. So the number density is the number of turns of wire per unit length. So the magnetic field of the solenoid is very strong when you have a lot of turns of wire in a short space. So when the number density N is very high or the current is very high, you have a strong magnetic field. But there's a limit to that, because at some point, if you put too much current through the wire, if it's a copper wire, the wire begins to melt because of Joule heating. So it overheats and melts. So there's a limit to that if you have copper wire. So at some point, if you wanted a stronger magnetic field, you have to go to superconducting wire. Okay, so with a superconducting wire, the resistance is going to go down to 0. You may have to, if it's a superconductor which requires cooling, then you have to cool down to helium with liquid nitrogen and liquid helium. You have to cool it down so that it becomes superconducting. That way you can have very high currents, and that gives you the high magnetic field. Okay, so that's what they do in the hospital magnet. A lot of those magnets have superconducting coils in them, and so that allows you to have a high enough current to have a strong magnetic field of about 1.5 Tesla.
Is that like a backup generator?
What is that?
What is that system for? Like you said for hospitals?
For the hospital magnet, the MRI magnet, they use a superconducting coil, a superconducting solenoid. Okay, so it's just basically a big solenoid with a space in it. If you've seen those before, so this is the space, this is the hospital magnet like that. And so they put a patient in, so this is the table, and the patient goes in there like that. Okay, so this is just a solenoid. Have a lot of wires in there like that. Okay, so it has, if you think of it, then it has a uniform magnetic field inside. So they put a patient in this tube, and in this space is a uniform magnetic field. So there are various things that you do then to create the MRI, the signal. It's basically a radio signal. So they create a signal in the patient, and the protons and atoms in the patient will vibrate and create a radio signal that some other receptor, some other coil will receive, and that is used to create an image. Okay, so this has to be superconducting. Lot of electricity, but basically what that does, what you're using that for is to cool. So you have to cool these wires, because once you get superconductivity, you don't need a lot of electricity to maintain the current, but you need to cool it down so the wire stays at superconducting levels. It has to be cooled to helium temperatures, down to minus 200 or whatever it is. It has to be cooled down so that it becomes superconducting. That way you have a very high current. That's what allows you to have the magnetic field. So this is just a basic MRI, magnetic resonance imaging. If you go to the junkyard, they have the coil like that. So you can use this to lift up a car. This is just the regular coil. This is not superconducting. So the field here will be, magnetic field is maybe 0.3 Tesla. So you can lift the car with 0.3. But this field is 1.5 Tesla. It's a very strong field.
No, it's so expensive.
It's very expensive. Yeah, that's right.
So those machines are measured in Tesla.
What?
So the
field?
yeah,
the magnetic field is measured in Tesla. 1 Tesla is 10,000 gauss. So the Earth's magnetic field is 0.5 gauss. It's very tiny, very tiny. 1 Tesla is 10,000 gauss. So the Earth's field is it 0.5 or 50? It's very small compared to this magnetic field. So when you work in the hospital around a magnet, you can't take any metal in, because if you take something that is metal, the magnet is gonna attract it, it's gonna fly, and when there's somebody in there, it's gonna hit them and kill them. There was some article in the news some years ago. There was a child somewhere, they were having an MRI. So the child is in there, they put this time, the head is turned this way, so they put the child in there. Somebody came in with oxygen tank because something was happening. So they brought the oxygen tank. The oxygen tank is going to be pulled right into the center of the magnet. So the child's head is here, the tank hits them in the head, and the child died. So the magnet is very strong. When I was in college, something happened, and one of these chairs, like this chairs, was pulled into the magnet. And when that happens, you can either quench the magnet or you have to pull it out. And if you take 10 men, you can't pull it out. Even with 10 people, you can't pull that. You have to use a winch. So we have to get a winch. And
Can't you just turn it off?
Well, you can turn it off, but it costs you thousands of dollars to ramp it back up. Because when you turn it off, then you have closed the superconducting, you've turned everything off. So they have to come back and fill the coils up again with helium and all that. It takes thousands of dollars. So we never turn the magnet off unless somebody's life is in danger. You never turn it off. So when that happened, we had to get a winch and attach the wires to the chair, and we had to winch it out slowly. Yeah. The magnet is very strong.
Oh, does it matter for the variable L if I use a capital L, or does it have to be?
No, it doesn't have to be. I just started off using lowercase l. That's why I used the lowercase, because I was using lowercase l here. So that's the solenoid. Let's do the toroid next. So a toroid basically is just like a solenoid. So if you take a solenoid, let's say you have wires wound around in space, and you just turn it on itself and hook it that way, that will make it a toroid. So the toroid is basically just wires wound around in a circle. Okay. So let's say that we can take a solenoid and make it into a circle by joining one end with the other, or with the other, to form a toroid. So with a toroid, we'll have something like this. Let me see if I can. So I'll draw a circle like that, and then I'll draw a wire around it this way. Okay, so that's a toroid. Okay, so if we think of the current going this way, I, if the current is going again that way, then the magnetic field is going through the toroid in this way. So this is the direction of the field through the toroid. If the current is if it's going into the board at the top and that way at the bottom. So that circle that I've drawn, we can call the Amperian loop. So we can think of a certain point here, and we say that this is a distance r from the center of the circle. And so at this point here, the magnetic field is this way. So by right hand rule, if I put my fingers in a direction, then my thumb points in the direction of the field. Okay, so the magnetic field is that way. And so a segment dl will be right here. So this time we use Amperes law again. Integral over the closed loop of B dot dl is equal to mu naught times the current enclosed. So the current enclosed is just the number of turns of wire enclosed multiplied by current I. Okay, so let's say there are n turns of the toroid. We multiply that by I, and that gives us the current enclosed. So integral of B dot dl, so the dl there is just the closed loop. So the integral over that loop gives us a circumference of the Amperian loop, which is 2 pi r, and that gives us mu naught n times I. So the magnetic field in the toroid B is just equal to mu naught n I divided by 2 pi r, where r is the radius of the Amperian loop in that toroid. Let's do one quick example. Okay, so I've given you a toroid of 10,000 turns, and the current is 5 milliamps, so the radius is 10 centimeters. What is the field of the toroid? Okay, what is the magnetic field in the toroid? So try to calculate that. 10,000 turns. Is anybody done with this?
I think so.
What do you have?
1 times 10 to the negative 4. Is that Tesla?
Yes, that would be Tesla. Okay, so you use B equals mu naught Ni divided by 2 pi r. So you're going to plug in mu naught, which is 4 pi times 10 to negative 7 times 10,000 times 5 times 10 to negative 3, and divide that by 2 pi times 0.1. So if that's what you did, then I'll go with 1 times 10 to negative 4, right? Okay, very good. Okay, so let's stop here.